Swayam Prabha. Digital India. Educated India.
Good morning and welcome to this next lecture on vibrations of plates and shells. We are in the topic of Rayleigh's method, okay, where we are using approximate functions in a minimization setup to find natural frequencies and mode shapes, and we have seen a few examples. Okay, now we are in an augmented topic, okay, a topic that is an addition to Rayleigh's, where what we have said is that suppose you have been working with a set of functions that are admissible for one system, and you have found them to be numerically stable in terms of matrix generations and inversions and so forth. Now that same system is slightly modified in the sense that, let's say earlier it was this cantilever beam, but now it is a cantilever beam restrained at one end, okay, restrained. Now it can be tricky to find admissible functions for the conditions here, and let's say you find them, this is a simple enough system, then they may not be good for numerics. Numerics may suffer. That is the next challenge, which is not so much the focus in this lecture. This is a basic set of lectures, but that is one thing you need to keep track of. And so the method we are looking at, which is the Lagrange multiplier method, is where you keep the original functions with you, okay, use the same functions, but because they do not satisfy these constraint conditions, for this problem they are not admissible strictly, they satisfy only partially one side conditions, okay. So we will stick with them. So what is it that we have? We have Wx of t, which is the mode shape vibrating freely at the natural frequency, and that special function is now a weighted sum of the original admissible functions which do not satisfy the constraint, okay. So we were taking an example for n equal to 2, okay. For n equal to 2 we have, first one is x over L whole square, second one is x over L whole cube, okay, and you can see that they satisfy the displacement and slope condition at x equal to 0. However, at the other end at x equal to L, what we end up is the displacement is g1 plus g2, which need not be 0, it has to be enforced, okay. So now what do? We have to enforce the constraint, okay. So we get an extra equation for the constraint. So you get one extra equation for the constraint, which is what? The displacement at L, okay, is what? Summation over j, let us say now 1 to 2, okay. Let me check, yeah, I am doing a case for 2, okay. So let me put n equal to 2 for now, I mean n now, n gj, that is equal to 0 if there are n terms. Okay. Then what are the other equations? The other equations are del Vm by del Gi minus omega square del psi m by del Gi plus del Gi. Now here we bring in Gn plus 1, which is actually the Lagrange multiplier. Lagrange multiplier. Okay, into f of L is equal to 0. Bring it straight here. Okay, and then what are my Vm's? The same original Vm. Vm is the same original integral 0 to L E I by 2 f double dash x squared dx, and psi m is integral 0 to L m by 2 f of x squared dx. Okay, so that results in hold on. So if you augment this set of equations with the last equation, which is Gn plus 1 into summation of Gj, j is equal to 1 to n Gj, and take the derivative with respect to Gn plus 1. Set it to 0. These are the new set of equations. Okay. So the original equations are here with this augmented term. Okay. Then you have the constraint equation that is differentiated with respect to Gn plus 1. Gn plus 1 is actually the Lagrange multiplier. Okay. So how does, I'll do an example for n equal to 2. For n equal to 2. Okay. So what is my f of x? That is equal to G1 x by L squared plus G2 x by L cube. Then what is f dash? F dash is twice G1 x by L squared plus 3G2 x square by L cube. F double dash is twice G1 by L square plus 6 G2x by L cube. Okay. Then what is Vm? Vm is the same thing, integral 0 to L E I by twice f double dash of x squared dx. Okay, and psi m is equal to integral 0 to L m by 2 f of x whole squared dx. Okay, so that after all the integrations, my Vm now looks like E I by 2 4 G1 square by L cube plus 12 G2 square by L cube plus 12 G1 G2 by L cube okay. And my psi m looks like m by 2 into G1 square L by 5 plus G2 square L by 7 plus twice G1 G2 L by 6. Okay. Now, the minimization equation. The minimization equation is del Vm by del G1 minus omega square del psi m by del G1 plus del G1 of the constraint equation G into n plus 1 f of L. Okay, what is f of L? G1 plus G2 equal to 0. Okay, so del Vm by del G1 is what? Is equal to Ei by 2 8 G1 by L cube plus 12 G2 by L cube. Okay, what is del psi m by del G1? That is m by 2 G1 L by 5 plus 2 G2 L by 6. And what is del G1 of G? So n is 2, so this is G3. Okay, so G3 G1 plus G2, this is the Lagrange multiplier. Okay, so that is equal to G3. Okay, so that's one for equation 1. Then equation 2. So this is equation 1. Terms in equation 1. Terms in equation 2. What are those? Those are del Vm by del G2 minus omega square del psi m by del G2 plus del G2 again G3 into G1 plus G2, that is equal to 0. Okay, so now del Vm by del G2 is equal to Ei by 2 24 G2 by L cube plus 12 G1 by L cube, okay, then del psi m by del G2 is equal to m by 2 twice G2 L by 7 plus twice G1 L by 6, okay. Lastly del G2 of G3 into G1 plus G2 is equal to G3. That's the second, okay, equation terms, okay. So let us look at that, the third equation. Third equation. Third equation. That is, what is the equation itself was G3 G1 plus G2. So we will have del G3 of G3 G1 plus G2 equal to 0, which gives me G1 plus G2 equal to 0. That's the third equation. This is the third equation. Okay. So if we write the three equations, this is the third equation. Third equation. If we write the other two, I have EI by 2 8 G1 by L cube plus 12 G2 by L cube minus omega square m by 2 twice G1 L by 5 plus twice G2 L by 6 plus G3 equal to 0. So this is actually the first of the equations. Then the second of the equations, EI by 2 24 G2 by L cube plus 12 G1 by L cube minus omega square m by 2 twice G2 L by 7 plus twice G1 L by 6 plus G3 equal to 0. These are the three set of equations. Okay. So now we will put them in a matrix form. So let us see how it looks like. We will deal with one with no omega square, one with omega square. Okay. So I have G1, G2 and G3. Here I have 4 EI by L cube, 6 EI by L cube, 1, 6 EI by L cube 12 EI by L cube 1, then 1 1 0. Okay, so these terms have been included, these terms have been included, these terms have been included. They are without omega square. Now I have the omega square related terms. So what are they? So minus omega squared then m L by 5 m L by 6, okay, then 0, then m L by 6 m L by 7, then 0, then 0 0, then 0. G1, G2, G3 is equal to 0. Okay, so this is the set of matrices you get for a cantilever beam plus a constraint on the right side. Okay. However, this set of matrices do not form a typical generalized eigenvalue problem. Okay, why? We had k times g earlier minus omega square m g equal to 0 as the generalized eigenvalue problem. I take an m inverse, so I take an m inverse, then k g, then I have minus omega square I g equal to 0, or m inverse k minus omega square I into g equal to 0. Okay, so this is like a minus lambda I. Let me stick to square brackets. A minus lambda I g equal to 0. So this is the eigenvalue problem. Okay. However, in this case, if I try to do an m inverse, there is no inverse here. You can't do it because of these zeros. Okay, it's just an augmented matrix. Okay, yet it can be solved. Here it can be solved. So you have a matrix now with all properties E, I, L, and M, and omega square, and you have G1, G2, and G3 equal to 0. Okay, then you can set the determinant to 0, then it will be a polynomial in omega square still and other terms. Okay, then you can solve it or look for zero crossings, solve this. solve for omega square 1, 2, 3 etc., omega square 2 etc. Okay, so those will, the zero crossings or the zeros of the characteristic equation, in this case characteristic are the new natural frequencies. Are the new natural frequencies. Okay. Once you have found this new natural frequency, let's say the first one, omega 1 squared, if you put it back into the equation, substitute back, okay, then the matrix is singular, because omega 1 square is a root, the matrix is singular, matrix is singular. Which matrix is singular? This matrix, or the combination of this matrix is now singular, and you have G1, G2, G3. So once matrix is singular, not all G1, G2, G3 need be 0. Okay, so then you find G1, G2 and G3. Okay, at least one of them will be in terms of the others. Okay, not independent. Okay, so then you have G1, G2, G3 values. Then you go back to your f of x, which is a linear weighted sum of Gj, this case J1 to 1 to 2. Okay, G3 is just the what shall I say, Lagrange multiplier, the penalty, Lagrange multiplier. Okay, the displacement itself is Gj into x by L into j plus 1. Okay, so the weights Gj are adjusted because of the constraint G3, and you will find that this displacement actually comes and goes to 0 at the restraint. Okay, so it is not a typical generalized eigenvalue problem, but it is numerically solvable. Okay. In the next class, I will show you the numerics on this one, okay, to show that indeed this method also works. Now this method is not a typical eigenvalue problem, so that is kind of a disadvantage. Okay, and it has some defects. We will look at some defects, and we will talk about another method which is called the penalty method. These are all augments to Rayleigh-Ritz method. Okay, and the whole problem comes because of the choice of admissible functions. See, at this classroom level it is difficult to appreciate. We are looking at n equal to 2 and n equal to 3, so that I can do it by hand, but suppose you are trying to estimate 1000 modes, or let us say even 100 modes, then your matrices will be of that size, 100 by 100 and so forth. Okay, and they may not be numerically amenable. Okay, so the choice of admissible functions, although it looks kind of trivial at this stage because we are looking at very standardized systems, Euler-Bernoulli beams with cantilever beams and simple constraints. But if you go to something realistic like a plate with some strange boundary conditions, then you will have to choose the admissible functions and they may not be amenable to proper numerics. Okay, so that's the thing. So penalty method is another method where you could again avail of some set of functions, not totally admissible, but on them you apply constraints, okay, and these constraints will put a penalty if they are violated. The more you violate, the more penalty, and therefore you kind of force them not to violate. Okay, so we will look at some of these in the coming classes. Okay, and these are all augments to the Rayleigh-Ritz method. Rayleigh-Ritz method. The base is Rayleigh-Ritz method. Okay, so I will close the lecture here. Thank you.